Hello. Before beginning, I want to thank you. I will present today my work entitled Prediction of Heat and Mass Transfer with a metal hydrogen reactor using the unstructured lattice Boltzmann method presented by me, Fatma Bouzgarro. I adopt the following outline. So I will begin by introducing the context, the problematic and purposes of the present study. Then I will present the CVLBM concept. After that, I will continue with the mathematical modeling and the numerical simulation of a metal hydrogen reactor during the desorption process. And I will present the results of my work, and I will finish this presentation with a conclusion. To begin, we can say that the hydrogen as a clean and inexhaustible vector has been the focus of recent researchers, and several techniques were developed to solve equations describing the heat and mass transfers in metal hydrogen reactors. Among these methods, a numerical method commonly called the lattice Boltzmann method has been considerably successful in simulating such problems, given its simplicity of modeling heat transfer problems, also its high performance in terms of stability and precision, and finally the easy handling of geometries and complex boundary conditions. But despite these advantages, the LBM remains restricted to sample configuration. This restriction is imposed by the manual generation of the mesh. In fact, for complex geometries, this meshing technique requires considerable time and effort, and even requires the development of a calculation tool for each configuration. In addition, for more complex configurations, taking into account all the limits, the calculation will be so heavy. Hence, we need to develop an unstructured mesh generation tool and a new numerical method by the conjunction of the LBM and the control volume finite element method while considering unstructured meshes. This new approach consists on solving the Boltzmann equation by the unstructured control volume finite element method. According to the following procedure, we subdivide first the domain into finite volumes, then we integrate each term of the Boltzmann equation on each control volume and over a time interval. Once the different terms are calculated, we assemble the algebraic equation obtained over the entire computational domain. Then we solve the system of equations obtained, and finally we calculate the macroscopic quantities by summing up all directions. The interest of the CVLBM comes from the fact that it combines the main advantages of the CVFM, such as its flexibility in treating complex geometries thanks to the unstructured finite element mesh, and the LBM such its simplicity in handling irregular boundary conditions. In the present work, the CVLBM is applied to study the coupled heat and mass transfers in a metal hydrogen reactor filled with the LaNi5 alloy, which exchanges heat by convection with a heating fluid through the base and lateral area. Our study is based on the following assumption. We suppose that the two phases, solid and gas, are in local thermal equilibrium and that the gas is assumed to be perfect. Also, we assume that the convective and radiative transfers are negligible and all the thermophysical parameters are constant. In addition, it is assumed that the pressure in the reactor is constant and the compression's work and viscous dissipation are negligible. Based on this assumption, the mass balance for hydrogen as well as hydride are written as follows, and the energy equation as is given by this expression. The CVLBM is adopted, and the Boltzmann equation, by considering the Bigica approximation, is written as follows, where S is the source term. Once we have all the distribution functions, we obtain the temperature by summing this function over all direction. Then we proceed to discretize the Boltzmann equation by calculating the terms Q1, Q2, Q3, Q4 and Q5. The discretization of Q1, Q3, Q4 and the source term Q5 are given by the following expressions, and by using the positive coefficient upwind CHIM, the SPCU CHIM, we calculate the term Q2, which the different coefficients are expressed as follows. So what about the initial and the boundary condition? So initially, the temperature and the hydride density are assumed to be uniform, and concerning the boundary condition, we adopt the following energy balance, assuming that the reactor exchanges heat by convection through its different area, and by using this equation and considering a linear interpolation, we can calculate the temperature at the node N as follows. On the other hand, the temperature at the corner of the enclosure is calculated by adopting the finite difference scheme. For this reactor, we begin by the validation of the numerical code. We compare the numerical values given by the numerical prediction and the experimental data of Gemini et al. Of the pressure when the reactor is connected to a tank of hydrogen. As shown in this figure, the results match quite well, which proves the accuracy of the new approach. Then we have plotted the temporal evolution of the temperature and the mass of hydrogen during the desorption process. We compared the results obtained by the present code with those of the CVFEM, the unstructured CVFEM. So we observe a good agreement between results, which proves the efficiency of the method. In addition, we can say that the CVLBM correctly reflects the hydrogen desorption phenomena, where the temperature drops at the beginning, then it increases due to the decrease of the kinetic reaction. Also, it is important to note that the computational time required to reach the steady state is equal to 42 and 4,420 seconds, respectively, for the CVLBM and the CVFEM using the same computer. Thus, it is greatly important to use a numerical method 100 times faster than the CVFEM. In addition, the evolution of the temperature along the axis of symmetry at different times is examined. The profiles obtained by the CVLBM and the CVFEM are in a good agreement. This concordance is well clear by plotting the isotherms at different times. In this figure, we note that the temperature is higher near the walls, which are heated by the circulating fluid, and by time the temperature increases progressively until reaching the temperature of the heating fluid. So, to conclude, we note that in this study, a numerical approach called the CVLBM, based on unstructured grids, is applied to simulate the hydrogen desorption phenomena. To verify its computational efficiency, the CVLBM results were compared with those of the CVFM, and we found that this approach correctly reflects the dehydrating process and has less CPU time compared to the CVFM, 100 times faster than the CVFM. And finally, let me thank you for your attention.